So, part one of Can a Newbie Build a Battery? Before I get started, I would like to explain a bit about what this battery is going to be used for. So, my goal is to eventually have a sailboat, blue water, which means being able to sail across oceans, but I want it to be quiet. I want it to be silent. I really don't like the sound of diesel motors. So, this battery is going to be the first of probably 4 or 6 packs, assuming I pull it off, that will give me a total of about 45 to 85 kilowatt hours of power for a boat in the 40-foot range, give or take, aiming for the 25,000 pound. I think that's 12,000 kilograms. I'm Canadian, I should be metric, proximity to America. So the idea behind this particular battery is that this pack will be 48 volts nominal, 280 amp hour capacity. If you're new to batteries like I was, amp hours is how many amps could you draw in 1 hour. So 280 amp hours means you could draw 280 amps for 1 full hour. Or you could flip it around and say you could draw 1 amp for 280 hours. So this one's going to be the first. If there's 6, then there'll be 6 times 280 amp hours at 48 volts. So these 16 cells are 3.2 volt each. Chain them in series, and you combine the voltage, but you keep the same amperage. So this is going to be, I think it's 51.2. I should probably have written this down ahead of time. Nominal volts. The next thing you need to consider when you're thinking about a battery is how many amps are you going to be drawing at the worst case? Something called the C rating, the maximum C rating. So a C rating is, I think, short just for capacity. I'll explain why it's the letter C. So at 280 amp hours, if I'm drawing 280 amps, I'm drawing 1 C. I'm using a 48 volt BMS, battery management system. A lot of fancy terms that don't actually, they're not as fancy as they sound. And this here has a maximum capacity of 100 amps, meaning with this BMS, the most I can ever draw on this is 100 amps. So at full draw, limited by this BMS, I should be able to drain this battery in 2.8 hours. Now, realistically, you don't want to run at 100% all the time. That's where things get a bit warm. But the benefit is even if I go to full power on that, one of the things that dictates how long a battery will last, how many charge cycles you get, is how heavily do you drain and charge it. At a roughly 0.35 C rating, I won't be draining these too hard. So part of my thought is by building a 100 amp hour maximum current draw battery, it means that even if I go absolutely all out over and over again, the battery should stay healthy for a long time. So the first thing you got to do when you're deciding how to build your battery is decide how you're going to orient it, decide how the bus bars are going to connect to it, and so forth. I don't know how I'm going to want these because I haven't bought a boat yet. I don't know how they're going to fit into the boat. So for now, I am going to go with a simple 2x8 layout like this. It'll keep it, well, as you can see, fits very nicely on my table. But I'm fully aware that by the time I'm ready to actually go and put it on the boat, I may have to rework this depending on where they'll physically fit, how I want the weight distributed in the boat, and so on and so forth. So for now, what I'm going to be doing is I had to pick first where is the main battery pack positive and negative. I decided to keep them at the front. Makes it a bit easier for this BMS that I'm using that has relatively short common and battery negative leads. So knowing that I wanted to have this configuration, I want this to be negative, I want this to be positive, building the battery is going to be a case of setting my bus bars here. So now this goes from 3.2 to 6.4. See how well I can do math here. And then I will do the next one, going from 6.4 to 9.6, and I'm going to stop doing the math now and continue on, so on and so on and so on. Obviously, you need the pin or the pegs, whatever they're called. And there. Now at this point here, if I checked the difference between here and here, I'd have a 24-volt battery. But I want to have 48 volt. So if I set this up to be similarly a 24-volt battery, let's see, that's going to jump over to there. it's going to become exceedingly apparent very early just how little I know about this. I'm not trying to pretend like I know how to do this. I'm trying to share what I've learned so far. Now, at this point, I'm effectively assembling this battery. There's not a great connection between the bus bars and the batteries, but there's a connection. So this is the point where you got to be really careful. There we go. So at this point in time, I now have two independent 24-volt batteries. Battery positive, battery negative of the first battery, battery negative, battery positive of the second battery. But like I said, I want 48 volts. And so for that, what I'm going to do is I'm going to take a couple of these ring terminals. I'm going to put one here, and there'll be a wire between them. And that'll connect the two 24 packs in series into a single 48 volt pack. Now, I am going to pause here and get these the heck off before I make a mistake. Now, the reason why you need to have a battery management system on lithium iron phosphate, which is what these are, as opposed to traditional lead acid or AGM type batteries, is that you need to be very, very careful about what voltage these batteries charge up to and how low they can discharge to. If you overcharge them or over-discharge them, you can badly damage the cell. Similarly, and this is important being in Canada, you cannot charge these batteries if they are below freezing. If you try to do that, they will damage the system or damage the batteries. So the job of the BMS is to make sure that it can monitor each individual cell voltage and it can monitor the temperature. So I've got them nicely tied up here, but I've got 3 temperature probes that I can put around the battery. If any of them show 0 degrees Celsius, or I believe I can set it a little bit higher, like 2 degrees Celsius, it cuts off the charging. What a lot of people will do, and I'll probably do as well, is you wrap them in silicone heating mats and you run that off of like a standard lead acid battery so you can warm the pack up. If you're somewhere where it gets below freezing, then you can safely start to charge the batteries back up. The second thing, and perhaps the more important thing, is in order to be able to monitor all of the individual cell voltages so that they don't drop below their minimum voltage or go above their maximum voltage, you have leads. Because this is a 16S16 batteries in series, I have a total of 16 leads. Each one of these, or is it 15 leads? We're going to find out. Remember how I had the bus bars here? Put a bus bar here, I will have a lead go here. And then I will have a bus bar here, and very carefully paying attention to what lead I use next, I'll have a lead here, and then a lead here, and a lead here, and a lead here, and a lead here. And at every connection between each individual cell, I have a lead. And what that allows the battery to do, the battery management system to do, is to calculate what is the voltage of each individual cell. So as the battery pack is charging up, when all of them are below maximum voltage, it's in something called bulk charge, meaning all the power possible is being dumped into the batteries. Once one of these cells hits its maximum voltage, that one stops being charged, and the BMS switches into something called absorption charging. Absorption charging is where a little bit of power is pumped out of each one of these leads. I can't remember exactly how much, I'll find it out later. And it will provide a little bit of power to the individual bus bars needed to charge an individual cell. And the idea behind that is you want to top balance them. Top balance is where you bring it up to the charge where it kicks in the absorption charge and you just let it sit there for a while. And as time passes, each of the individuals are all brought up to their maximum voltage until all of them are the same voltage, and then the charging stops entirely. Now, similarly, when you're discharging it, this is able to monitor each of the individual cells, and as soon as any one of the cells drops below the minimum, it cuts off power from the entire battery so that you can't accidentally drain the thing too much. Now, normally the way you would connect the BMS balance leads, that's what they're called, to a battery is with a ring terminal. Let's see if I can find one of the ones I had. I probably should have dug it up before I started the video, but I didn't claim to be a professional videographer either. So the problem I had was that you can see these wires are very low gauge, 22 gauge, 24 gauge, something like that. So I had to get these itsy bitsy little, you probably can't see that, itsy bitsy little ring terminals. And I ordered them and they didn't fit over the post. So then I ordered another batch. They also didn't fit over the post. It should be pretty obvious by now that I'm learning this as I go. So rather than buying a third set of ring terminals, what I've decided to do is I am just going to drill a hole through these. I'm planning to replace these. These are, I believe, aluminum. Any case, I plan to replace these bus bars with a little bit thicker tinned copper bus bars. Everything on boats you want to have tinned copper, otherwise it's going to corrode. So for now, because it's simple, I'm going to drill a hole through this, and then I'm just going to, I don't know where I put them, run a bolt and a nut through the middle of the bus bar and run the lead off that way. Screws and bolts that are going to fit this properly. It'll be ugly, but again, this is my test battery. This is me learning how to do this. Everything's going to be torn apart and reworked whenever I finally get a boat. Now, that's the basic design of the battery pack itself. We need to have, very first off, safety. So what this is here is what they call a T-class fuse. I'm going to keep saying this, but I didn't know what that was more than a month ago. A T-class fuse, these batteries have so much power in them that if you created a dead short, a traditional fuse would blow, but there's enough power that it could actually create an arc, a plasma arc, across the two fried terminals and not actually break the circuit. So a T-class fuse, what it is a fuse, obviously, but it's filled with silica sand. So if anything ever happens and the current going through this, I think this is set to blow at 120 amps, I'd have to check. Nope, 200 amps. 200 amp T-class. It's really good that I know what I bought. If more than 200 amps gets drawn through this, it'll blow, but the sand will then break the arc. So I believe these are high discharge, high current, something, something, something. They get sand to break the arc. So that is going to be our primary safety device. The BMS has its own internal overcurrent protection that'll cut off, but this here is something very, very bad has happened. If you blow this thing just saved your life probably, or at the very least saved your eyes. Oh, and one thing I should mention, you'll see that when I'm ready to actually start working on these, I'll be wearing glasses, safety glasses. The reason for that is, if you short something, even if the fuse blows, there's enough power that it could actually vaporize some of the metal in whatever you shorted it out with. That could send molten metal, copper, whatever, flying. You get that in your eyes and yeah, I'm not sailing. So I will be wearing safety goggles for that when I actually get to the build. So the next piece we're going to need is a smart shunt, Victron. I'm going to be using a lot of Victron gear in here. So again, I had no clue what this was. I had no clue about anything. What this does is you tell it when you have a full charge in the battery, and then you drain it down to complete empty, and you tell it that it's done. I'm not exactly sure how you tell it. It's a Bluetooth app, so maybe it just figures it out by itself. In any case, the smart shunt is able to learn how much capacity is in your battery. And then from that, you're able to connect either over what they call their VE direct cable, which I do plan to be using, so you can hardwire it into a monitoring service, or use your phone to see what is the state of charge of your battery. One of the things when people who are familiar with traditional lead acid AGM batteries, as I was, you're used to being able to use the voltage to be able to decide what is the state of charge. With lithium iron phosphate, the voltages are very consistent. So when you first start to discharge the battery, they drop, and then they hit a steady state, and they hold that steady state pretty much entirely until the end of the charge cycle, and then the voltage just falls off a cliff. So you have to have a little bit more smarts to be able to know what percentage of my energy is still left in the batteries. And that's what the smart shunt provides you. It's basically, as I understand it, you connect this onto the negative side, so the same size as the fuse, which I will show this if I can figure out how to do that in video editing. It's a chart to show where all the pieces are going to go, but it's going to go BMS, smart shunt. Oh, I was wrong. See, I told you I'm new. This goes on to the negative side of the battery so off the negative BMS to the smart shunt and out, and the fuse goes on the positive side. Now, there's one more part of this battery that's going to be set up, and that is this, a pre-charge resistor. So the idea here is you have your main battery disconnect. You're going to notice it's all marine gear. Like I said, it's going in a boat. If you are building this for non-marine environments, you'll save a lot of money by not getting marine gear. Anyways, this is a marine battery disconnect. When you are about to turn on the battery, connect the battery to the load, if your load is an inverter, they've got really big capacitors in there. And when you turn it on, you could get an arc. You can get a spark, basically. As I said, there's a lot of wonderful YouTube channels out there, and the Off-Grid Garage designed this, or someone he knew helped him design it. What this is a push button. Probably can't hear that. Oh. It's a push button that would create a connection around this switch. But because it's a resistor, it doesn't allow the current to flow super fast. So the idea behind this is when you're about to connect this to the first time to a inverter with big capacitors, you'd press and hold this button for a second, and it allows the current to bypass this switch and pre-charge the capacitors. So you hold this down for a couple of seconds, it charges the capacitors, then you turn the main switch and your battery's on and your inverter is charged. I will be using a Victron Quattro, blah, 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 more details later. So that is now the basics of the battery pack. We haven't talked yet about the solar charge system or the inverter charger or any of that other stuff. That'll all come later. But this is an overview of how this battery will actually be built. It's going to be fun. Terrifying, but fun. So there's build video 1, I suppose. Let's get started.